Hi, my name is Anthony Yu, and this is my Lab 5. So, the introduction. This lab was about Faraday's law and how it relates time-varying magnetic fields to a Curly electric field that drives a current through an EMF. The falling magnet in this lab that we let fall through the aluminum tube represents the external field, and the aluminum foil represents the induced current, and their interactions were observed. Also, we created a computational model of the falling magnet through the roll of foil and calculated the current induced by each ring, the force on the rings by the magnet, the force on the magnet by the tube, the net force on the magnet, and also plotted a velocity versus time graph at the end. The materials needed for this lab were a meter stick, smartphone, a roll of aluminum foil, and a bar magnet. So as I said before, we dropped the magnet through a roll of aluminum foil and recorded the time it took for the magnet to enter and exit the roll of aluminum foil. And we repeated this 5 times and took the average. These two equations on the bottom right, the first one is Faraday's law and the second one is Lenz's law. It's just a couple of laws that we've used in this lab. So my actual data, the length of my aluminum tube was 12 inches or 0.3048 meters, and the mass of my magnet was 0.035 grams. For me, the time taken for my magnet to fall through my aluminum tube was an average of 1.286 seconds. And it takes much longer to fall through the aluminum foil tube when the magnet is dropped with this north side down compared to its south side, as when it's dropped with this north side down, it creates an induced current in the counterclockwise direction in the tube, and thus this induced current in the tube creates also an induced magnetic field that points upwards, basically the opposite direction of the magnet falling through the tube, and resists the fall of the magnet through the aluminum foil. If the magnet was dropped with its south side down, the opposite would happen, a clockwise current, and the induced magnetic field would point downwards and would help the magnet to fall through the tube. So my code output. As you can see, the first graph on the top was my code output with the mu mag value that I took from lab 3, which gave a time in tube in seconds of 14.076 seconds. And also, as you can see, the velocity versus time graph or the plot looks very wrong. I think it was just because the mu mag value that I got from lab 3 was much, much larger than it was, or than it was supposed to be, to get the correct results for this lab. And so changing my mu mag value and decreasing it to a much lower value of 2.19 gave actually a much, much more accurate result, which gave a time in tube in seconds of 1.281 seconds, which is actually just like 0.005 seconds difference from my average experimental value. And as you can see, also comparing the two velocity versus time graphs, the one on the bottom looks much more like it should. You can see the velocity decreasing and then increasing, and basically zeroing out, not zeroing out, but not increasing or decreasing, just keeping a constant value and then slowly decreasing again at the end. So the final questions. What if the resistivity of the conductor were reduced as close to zero as possible? How would the dynamics of the falling magnet change? Well, I thought that if the resistivity of the conductor were reduced to a value as close to zero as possible, then the magnet would experience much more opposing force while falling down the tube, as the current in the tube would experience less resistance, and thus the induced current in the tube would be much stronger. And because the induced current in the tube is much stronger, therefore the induced magnetic field would be much stronger, and the magnet would take much longer to fall through the tube. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, if holes or slots were cut into the tube, the eddy currents or the induced currents that allow for the creation of the induced magnetic field that resists the falling magnet, and therefore creates the effect that we see in this lab, would not be created by the tube, and thus the magnet would not fall slowly through the pipe. There would be no opposing magnetic field. It would just fall as if you were dropping it in just normal air. And that is my lab 5. Thank you.